Hey, welcome to Pomodoro Joe for Tuesday, October 17th, 2023. Today we're looking at LeetCode problem 1361, validate binary tree nodes. This is a medium problem. So, you have n binary tree node numbered from 0 to n minus 1, where node at I has two children, left child index I and right child index I. Return true if and only if all the given nodes form exactly one valid binary tree. All right, so basically we're given a certain number of nodes, n, and we have two arrays, a left child array and a right child array. Now the index is the node number, and the value for each of these arrays will be the left child or the right child. All right, if node I has no left child, then left child index I will equal -1. Similarly for the right child. All right, so if we have an array where there's a -1, that means there is no child on that side. So left child, this is going to be, let's see, index 1. It's got a -1, so node 1 has no left child. All right, note that the nodes have no values and that we only use the node numbers in this problem. So this is kind of interesting. We're not actually given a real binary tree node. We don't actually have a structure of a binary tree node. We're just given these node concepts. So the node has a number, but it doesn't actually contain any value. So the node will be numbered 0, but there's no value for this node. All right, now the node's number is the index into the left child or right child array, or and right child array. And the value in that array will be the left child node number or the right child node number. So for example, we have n is 4, left child, so node 0 has a left child that's node 1 and a right child that's node 2, as we can see here. And then node 1 has no left child because it's -1, and it has no right child because it's -1. So there's no child nodes on node 1. Then node 2, we have one left node, which is node 3, and we have no right node, -1. And then we go to node 3, and it has -1, -1, so it has no nodes. All right. Okay, let's see here. All right, so let's put 25 minutes on the Pomodoro timer and we will get started. Now, I'm not totally sure how I'm going to do this one, but we'll try it out. All right, here we go. So, how am I going to solve this problem? Well, let's see. I think the first thing I want to do is find the root node. Which one of these nodes is the root node? So let's start with that. So find the root node. All right, and how do we find the root node? Well, the root node should have no nodes that point to it as a child. So if we go through all of our nodes, all these left child and right child nodes, there should be one number that is in our n group that doesn't exist in either the left child or the right child. That means it is not a child of any node, and that should be our root node. So let's see, how do we find this? I guess I can go through both left child and right child nodes, or I could maybe use a set. I think I like that. Let's try that. So we'll have all nodes, or all child nodes. How about that? So all child nodes will be a set of all the child nodes, and that's going to be the left child list plus the right child list. Okay, so I'm going to take the left child list, extend it with the right child list, so basically smush these two lists together. Then I'm going to create a set out of that, which is just all the unique values. So the left child, the right child, we create a set. Those are all the child nodes. Now I'm going to create a new set of all the nodes that we expect. So I'll call this all nodes. And that's going to be a set of the range from 0 to n. So the range from 0 to n will actually count from 0 up to n minus 1, up to and including n minus 1, and then it's going to put all those numbers into a set. So this should be the set of all the nodes. Now to find the one node that's the root node, so I'll have the root node set, and that's going to be the all node set minus the all child node set. And so this will give me a set, and there should be one node in there. And if there is one node, that will be our root node. If there's more than one node, then we have a problem. And if we have fewer than one node, then we have a problem. So let's do that check first. So if the length of our root node set is not equal to 1, then we can return false. There's a problem. Otherwise, we can get our root node out of it. That's going to be the root node set. And we have to pop it out. So we'll do a pop. All right, so this root node set has one node in it. We're going to pop it out, and that is our root node. Now that we have the root node, let's just go and traverse our tree. And we'll keep track of whether or not we've already seen a node before. So we'll traverse our tree. We'll keep track of the nodes we visit along the way. If we see the same node twice, then that's going to be a problem. That means that we have this same node being pointed to by two nodes. So let's see, we'll have our queue here. So this is the nodes that we still need to visit. And we'll start our queue with the root node. We need to visit the root node. All right, and we also want our visited set. That's just going to be an empty set to start with. All right. And now while we still have nodes we need to visit, so while our queue, we'll grab a node out of the queue. So the node will just equal queue.pop. I'm going to pop it index 0, but you can pop it index -1. It doesn't really matter. All right. Now, if this node is in our visited set already, well, then we've seen this node, which means that it has two parent nodes, and that's a problem. So we'll return false. So if node is in our visited, looks like I misspelled this. Let's fix that here. All right, so if node is already in our visited, we'll return false. It has too many parents. Otherwise, we're going to add this node to the visited because it's not already in there, and we are visiting it right now. So visited.add this node. And now we need to visit this node's child nodes. So let's check to see if left node for this node left child. So if the left child for this node, if this is not equal to -1, so if the left child node is not -1, then we will add this child to our list, and this is the next node or one of the next nodes we're going to visit. So if this node's left child is not -1, that means it actually has a left child node, and we'll add that node to our queue because we still need to visit this node. So queue add or append, and let's see, it's just going to be left child for this node. And we'll do the same on the right. So if the right child node, the right child for this node is not equal to -1, it has a right child, and so queue.append right child for this node. Okay, now if we make it through all of that and we didn't return early because we ran across the same node multiple times, then we can return true. Actually, is that true? I don't know if that's true. What if there are nodes that are not connected to any node? I might need to do some extra checking here. We'll return if the length of our visited, I like this. So if the length of our visited, that means we've visited all of these nodes. If that is equal to n, that means that we have all the nodes in our tree. Cool. Okay, I think this is right. Let's try this, see how we do. Seems to work. Let's see if we can pass all the tests. And we pass. And let's see, we don't do great for memory, but we do okay for runtime. Let's see. We do 69% for runtime, 43% for memory, so that's not too bad. And looking at this, we're actually in the upper range, so yeah, not bad at all. And it looks like very similar solution. They did something similar. Their set's a little bit different. I did a subtraction. They actually went through and looked for each node. Very similar kind of thing. They're using an array for their visited instead of a set, but it's very similar. All right. So I think that's about it for me. Let's see, we probably could go through and optimize this, but I'm actually pretty happy with the solution. So I think that is it for me. All right, well, I hope you enjoyed this. I hope you had fun. I hope you learned something. I hope you can go out and write better code.